Okay, so I'm going to be talking about substructure and accretion dynamics today. This is a kind of aspect of galaxy formation. Is this working? Yeah, it's working. Galaxy formation that I've gotten interested in lately. I'm going to start off with a video from the Durham group. Apologies to local people, but this is one that I really liked. If you could see it, this is the cosmological buildup of the stellar halo of a galaxy. And what they've done is, this is based on the Millennium, well, it's the Aquarius simulation, and they've done some kind of particle tagging of star particles. And what they've done here is that you don't see any of the star particles in the main galaxy, so this is just the pure accretion component of the stellar halo. And you know, as you all know, in lambda CDM, you've got the hierarchical galaxy formation with things falling all the time. You're used to seeing these as dark matter simulations probably. This is just showing what you expect to see in the stars. And there's a lot of structure you expect to see. You know, every point in time, there's things continually falling in. Like the analogy of buzzing bees continually flying around and falling in, and seeing a lot of substructure. And the idea is, if this is the correct model, then we should be able to go out and see all these substructures at, for example, at low redshift where they're easier to see. And there's a lot of work done on this in the Milky Way in great detail. We've got the Gaia satellite that's going to be going up pretty soon, and one of the ways of looking at the Milky Way halo. So, and now it's fixed, now down to redshift of 0, just rotating around to see the substructure here. There's some shells there of some object that's falling in on a radial orbit. So the idea is to try to see how can we observe these substructures in the local universe, how can we model them. There's just a nice example there of an observed shell galaxy, and there's been a lot of those observed over the years, and they just kind of fine-tune the simulation a little bit to match that observation. So the questions we want to ask are, how do the substructure observations compare to the predictions? And so this is slightly different. There's a lot of work done on dwarf galaxies, surviving dwarfs in the halo of the Milky Way and other galaxies, too big to fail problem, et cetera, et cetera. This is the dwarfs that are disappeared or in the process of disappearing, and to test those predictions as well, the numbers, the masses, orbits, metallicities. And is there any connection between the types of substructures that you get and the galaxy type? Are spiral elliptical galaxies, do they differ because they have different infall histories, for example? And can we use those substructures as novel methods for constraining the masses of galaxy halos, and as has been done in our own galaxy with a Sagittarius stream, for example? So speaking of our galaxy, and here's a couple of familiar things. The field of streams on the left, it's the Gaia satellite, and there's a model of the Sagittarius stream. But the Milky Way is not the universe. Whatever we learn, however many billions of dollars are poured into these projects to understand the Milky Way, you ended up with a sample of one galaxy, one type of galaxy, one environment. You'd ideally like to do this in more galaxies. You can go a little farther. If I don't know if any Splash people are in the audience. There's great work been done on M31 and a lot of dynamic accretion stuff happening there. But still, the local group is not the universe. We want to go farther, get the statistics of substructures over the full range of galaxy masses, types, environments. Okay, it sounds pretty difficult, but let's try. So first is just a point of reference is, what do we expect? If we're going to go out and try to look observationally for substructures, what do we expect from theory? And I've kind of crossed out substructures there because there aren't many predictions, and that's what I encourage people to think about if you're interested. There's a lot of kind of general accretion predictions for galaxies, but the more specific ones of what types of substructures you expect have been really geared toward the Milky Way for obvious reasons, because that's where we've got all these observations happening. But in generically for other galaxies, elliptical galaxies, for example, there aren't the predictions. But just to go through a few basic predictions, and this will be old hat for a lot of you, but one of them is that the accretion history in terms of mass of most galaxies is dominated by about 1 to 10 mergers. So you should find evidence in most galaxies for at least one to 10 merger in the halo at some point in their history. And the time scales on which you expect to see that is about 1 in 10 galaxies have had one of those in the last 2 gig years. Okay, just to get that in. And I see Kyle here. This is actually your work. And that this increases with host. So on the bottom axis here is the host mass. As you get to more massive halos, you should get more stronger accretion. So the place to look for it, and this is broken down in terms of the older accretion events and the newer accretion events because the halos build from the inside out. The place to look in the low redshift universe is the outer halos, and here it's in outside of about 30 kiloparsecs is where you look for recent events. Now this is kind of some new interesting work just trying to do semiotic models to see what you expect as a function of galaxy type, and they as you might expect, because early type galaxies are in denser environments, you also expect stronger accretion histories. But this is the first real prediction I've seen for this. There might be others out there, but the first I've seen that predicts that elliptical galaxies should be more accretion dominated than spirals. Okay, what about observations? What's been done, there's actually surprisingly a lot has been done in terms of trying to survey and get statistics of substructure photometrically of other galaxies. And I've put up little thumbnails of tons of things that have been done over the years, starting back with Malin and Carter 30 years ago now. And found a lot of interesting stuff, but a lot of it's been kind of like stamp collecting so far. Kind of, those are like postage stamps, and it's not been easy to understand what it all means. I mean, this Atkinson et al. Did this nice review where they tried to summarize the findings to date, and their substructure fractions galaxies ranging from 3% to 70%. So it's sort of almost, it sounds almost meaningless, those kind of numbers, that range of numbers. Well, part of the issue is it depends on what type of galaxy you're looking at, how deep you're looking, what the environment is. We expect some variations, and so that hasn't all been teased out, how those systematic variations, how much of that is just some observational error, how much is systematic variations with these other parameters. So that's something we're working on, which I don't have anything to show on that yet, but here's one interesting thing that Atkinson found in their particular survey, which was the CFHT lensing survey, I think. This is the familiar red sequence blue cloud plot, and the points here are the ones with substructure, this certain type, I forget, this was fans. And generically they found that the early types had twice as much substructure as blue, so as you would expect from the theory, at least qualitatively. So early types has been, and most of you have probably heard of this many times by now, are the subject of a lot of interest with two-phase galaxy formation. Which is this idea originally motivated by observations that these galaxies start off very compact at high redshift and are much more extended today, and the idea that is because of a second phase of infall, accretion, building up the stellar halos of these galaxies. So the most extreme cases of these ought to be the brightest cluster galaxies. And they've got these very extended envelopes, say CD envelopes in some cases, and the question is, where do those come from? And they're thought to be, again, the second phase of galaxy formation. And here's one semiotic model of a BCG where it's classic downsizing. You got this early star formation, and then the assembly is happening much later at late time. So about half the mass has accreted in the last 5 gig years. So those are the places, if you want to see active accretion happening, those are the places to really look. 10% of the mass every 1 gig a year. And the question is, well, so what do we look for? I mean, a lot of these galaxies look like, sometimes you see active mergers happening, but not too often. They're a small fraction. But you want to see, okay, is there some way to see recent mergers or accretion events happening in these galaxies? Well, what you can do is go past configuration space. So here's some sample star particles in X and Y on the sky. And go to phase space of position and velocity. And this is some toy model where you can see very tight, cold stream in phase space. If you could go make velocity measurements. And you could even go beyond that, do some kind of dynamical model and pull out, say, the integrals of motion. And things can really clump up in distribution function space, for example. And here's a kind of a quasi-real example from a book simulation of accreting satellite galaxies. So you can see these cold streams in phase space. Now, one of the issues here is that this is idealized. It's in it's quasi-static potential, very smooth. It's not truly cosmological. So you'd like to know, how long do these things stick around where you can detect them? And there's been a little bit of work done on that. Chris Mijos' group with Craig Rudick, they looked at some live cluster buildup simulations, and they found that very generically the substructure persists for about 1 to 2 dynamical times before things like time dependence of the potential, basically other substructures and phase mixing all wipe it out. This is an example from some recent simulations from Severino, cosmological simulations where I just wanted to have a look at if does this work. This is the buildup of a massive galaxy at redshift of 2 to 1. And these red particles are the ones that are just a sample accretion event. At time of 0, after 3 dynamical times, you can still kind of see it in phase space. And then after this 30 dynamical times, it's all mixed in. Okay, this kind of goes along with these Rudick expectations. So the idea is we're looking for something that's happened within a couple dynamical times. And so what are the dynamical times in a real galaxy? Here's a sample L-star elliptical. In the center, it's say 30 megayears, then 150 megayears at 10 kiloparsecs. And then you get out to about 40 kiloparsecs, you start getting into half a gigayear. And those are the kind of, if you remember the timescales at the beginning, that's where you start to expect action to have happened in a fair fraction of galaxies. So that means if you look on this, where you can observe with stellar kinematics, with Sauron, you're not going to see things. We've got you'll hear a little bit later from Gene Brody about some stellar kinematics go out farther. It's still not far enough to see things typically. You need to go out into the outer halo, and the question is then how do you observe stars in the outer halo, at least spectroscopically? And the answer is you have to use tracers right now. In most cases, I'll show you another example where you don't. And planetary neighboring globular clusters will get you out there. And you need also high precision to see these cold streams. So here's an example. That's all the intro. Now I'll start getting to some results, although a lot of this is kind of new work that I don't have a lot of results to show, but this is one with results. This is a famous galaxy M87, nearest BCG. And that's this little picture. If I blew it up, you might recognize it. It's about 20 kiloparsec scale there. What happens if you look at the stars photometrically at larger scale, 150 kiloparsec? This is you've probably all seen some version of the MIHOS pictures over the years with the Schmidt telescope. This is a new version of that, and it looks quite different. In fact, if you looked at a galaxy like this, you might not call them elliptical galaxies. You might call them rectangular galaxies. I'm not really sure what's going on there, some kind of box orbits or some interesting effect of sharp orbit features. It hasn't been modeled yet. And part of what you can see over on the right, there are some small accretion events, and we've targeted those spectroscopically and seen some things happening interesting. But those are very small, we call mini minor mergers. But we're looking for things like the larger events. And what we've done is we've got a large spectroscopic sample in this galaxy, high precision. This has been a favorite galaxy over the years, but we've done vastly improved on this. And to get to the point on this, here's a phase space plot for globular cluster velocities. This is from the slug survey, which you'll hear next from Kristen Woodley and Gene Brody about some more of this. But I hope you can see there's some little triangle there in phase space, which we've done all sorts of statistical tests to make sure it's real. And this is a classic signature of an accretion event making a shell. It's been seen photometrically, but never in one of these galaxies seen in phase space. Here's our little quasi-in-body simulation of the event. Small galaxy falling in and creating this caustic feature in phase space. And it has to be a very radial orbit to make this happen. So we're able to model this, and I won't go into it. Kind of the theme of the rest of the talk is going to be, okay, we kind of are able to start modeling these things in some very broad sense, but when you look at the details, they get very confusing and, well, very interesting for modeling purposes that the numbers don't quite work out on this. It seems to be a lot of globular clusters. It should be a high mass galaxy, but it seems to be a very cold stream, which is more like a low mass galaxy. So some more work to do on that. So back to this theme I mentioned earlier about measuring masses. So a lot of times we've got these large surveys. You'll hear more about this from Kristen. Large surveys of globular cluster kinematics to measure dark matter properties. And people ask, well, how many velocities do you need? 100, 200, 1,000, and you need a lot. And so generically, what we're doing when you'll hear about this modeling, it's kind of all methods based on statistical mechanics coupled with Newtonian gravity and things like taking moments of the collisionless Boltzmann equation. So you're having to use lots of velocities because you're having to do this statistically and statistically build up this distribution function. This is kind of like this is one way using Schwarzschild modeling of how many velocities do you need. It's that little formula delta m over m. So let's just say for 250 velocities, you can get a mass measurement good to 20%. So that's sort of what we're looking at, 250 velocities. But you don't really need 250. All you need is one. Yeah. You just need one where you know the orbit, you know the position, and you need the 6 dimensions of phase space of that one orbit, and then you can get the measurement. So that's the other approach we're trying to do. This is classical mechanics getting away from that whole other approach with all the degeneracies. Now, of course, this has its own set of degeneracies, which, as we start working on this, we find out pretty quickly could be an issue. So here's one example of using the shells to measure the gravitational potential. I showed you before these chevrons in phase space, and that's the idea that at apocenter you're at 0 velocity. As you dive inwards, you're gaining the potential energy, and all you're doing is measuring. So you're losing potential energy, gaining kinetic energy, and all you're doing with observations is measuring that increase of kinetic energy as you go in. It tells you your gravitational potential difference, and you could do different formulas for this. So it seems pretty straightforward. Problem is when we go out and try to do it on the observations. Like on M87, there's some numbers that just don't make any sense. It's sort of too high, too low, too rapid of a change. So in practice, this simple approach didn't quite make sense. And it turns out there's lots of different effects you start after thinking about, things not being spherical, not being perfectly radial orbit. And people have started working on this. Robin Sanderson, who, me and Helmy have had a nice paper out now where they've got some semi-analytic methods for modeling this, and we're going to be applying this to this data to see if we can extract the information more accurately. So another example, so that was sort of BCGs. Now in the realm of L-star spirals, this is another galaxy called the Umbrella, and you can see a stream there. So this is interesting. It's a Milky Way analog with a Sagittarius stream analog. Like almost everything about it is the same. The difference is we're seeing it from the outside. And this has been known for a while, but now we're going in and doing spectroscopy of it. And one of the first things we found out is that this seems to be the progenitor nucleus, or at least it fits in really well with the velocity and everything to make sense for this being the nucleus of the dwarf. And we've got kinematics of globular clusters, planetary nebula around this thing. And we're starting to do modeling of the orbits to figure out what the orbit of this thing is and constrain lots of things. But again, what we start off, the simplest thing you could do is a single test particle, say track that nucleus. And when you start trying to do that in detail, you find you can't match anything. Or you can match one bit at a time, but you can't match everything at once. Because again, there's all these effects going on, like different binding energy of different stars in the progenitor. Here you can see an example, a face-on picture of the simulation where the apocenters of the in-body simulation are not on a circle. And that's, otherwise it's a spherical potential. They're interesting things. They're complications that we're starting to grapple with, and we need better models for dealing with that in a simple way. So, we've got a bunch of galaxies we're surveying now. I'll just skip over that, doing the spectroscopy of it. Let me just skip over some of this stuff since I'm running out of time, and go to the final, get into the realm of dwarf galaxies. So this is an LMC analog. People who study starburst love this thing because it's a starburst-iest galaxy in the local universe, NGC 4449. And there it is from HST. So we've got this wide field image from Subaru of resolved stars, kind of like you've seen in M31 in the halo. And you can probably kind of see it up in the upper right there is this new thing that popped out. It's a dwarf spheroidal being accreted by this other dwarf galaxy, a dwarf goblin and a dwarf. First time something like this has been seen. Although, again, from that video in the beginning, if lambda CDM is roughly scale-free, then we expect this to happen, the dwarf galaxies to be accreting smaller dwarfs. We just hadn't been able to see it before. There's a little zoom in where you can see the resolved stars on this. So this is one where you can actually start getting individual stellar kinematics, which we've done. Have some summer students working at this point. So one of the things that gets interesting here is, I don't know if anybody's going to be talking about the too big to fail problem. A lot of that is trying to tie dwarf galaxies to their halo masses, and based on observations like in the centers, but you'd like to know what is the real halo mass. And when you get something like this, you've got the dynamics of an accreting object, you can start constraining the total mass of that without having to do all these extrapolations. And this is a little video from Elena Dongia of this trying to pin down the orbit and then the effects on the main galaxy. So again, this is work that's still in progress. I can't give you results yet on what we think the dark matter mass is of this dwarf, but we're getting there. If I can cut out, just get to the summary. And okay, don't ask me about red nuggets, or ask me if you want to know. So I'll just leave up the conclusions of, and we expect streams and substructures to be in all sorts of galaxies, as well as our Milky Way. And let's go out and look for them, and that's what we're doing spectroscopically in metallicity. And like we need more like specific predictions on, now that we're getting all this data coming in, more specific predictions of what we expect from Lambda CDM, how we can constrain that, or some of these alternative models that are out there, self-interacting dark matter or whatever. And as we're doing the dynamics of these things, we need better and more improvements on the dynamical models, ways to simplify the modeling methods without doing these very expensive in-body models. So thanks for your attention.
Questions for Aaron? Starting with Joel.
One of the things that we've tried to do with the Sagittarius and other streams around the Milky Way is determine the shape and other properties of the halo.
Mm-hmm.
And I assume that that's one of the main goals of not just measuring masses, but more properties.
Mm-hmm.
Any progress?
Yeah, right now we're just working on getting like the zeroth order, the mass, or sort of the circular velocity at a given radius, and then we'll have to go to the second order of what is the shape. So we're working on, I mean, I hope so. And we don't have as much dimensions of phase space that we're getting. We're only getting 3 dimensions instead of, up to 6 in the Milky Way. And as you probably know, there's still a lot of debate about what we've learned from the Sagittarius stream, and every year it seems to go to a different answer. So
even the same author, Law,
yeah,
has 2 different papers the same year with 2 different answers.
yeah, yeah.
Other questions? I have one and a comment.
Mm-hmm.
NGC 4651,
Mm-hmm.
the Milky Way analog.
Mm-hmm.
You have a Vmax scale length for it?
Mm-hmm. Yeah, I don't.
Which are, how do they compare with the Milky Way?
They're similar. That's why I kind of said that. I don't remember the numbers. I think about 200 kilometers per second.
And the scale length?
And the scale length, I want to say like 4 or 5 kiloparsecs, but I don't remember.
Okay.
Yeah.
Presumably a similar stellar mass and dynamical mass.
Mm-hmm. Mm-hmm.
The comment is a reference that you made to Cooper et al. 2013 as being one of the first evidence for accretion, right? Earlier on, when you showed basically the ratio, do you mind going back, the ratio
Sure.
of inner mass, inner halo mass to total as a function of total mass? And I was curious about that reference, and you'll see why in a second when you show it.
Yeah.
And maybe I'll invite Christine to come up. Yeah, that one there. Who's? I tried to look it up. This one. So it's the ratio of accreted stellar mass, right? How much you were totally accreting over the total ultimately. And I cannot find this reference. I tried very quickly.
Oh.
I'm a little surprised. This is a carbon copy of Figure 10 in Courteau et al. 2011. Identical.
Okay.
And so, in terms of first, I was stunned by that. So, have a look.
Okay.
Have a look, okay? 2011, perhaps that I would say is the first evidence for mapping accretion in M31 and the Milky Way. Absolutely identical. So,
Did you have early?
to follow this.
Did you have early types in there too?
No, not Stefan Cooper. So I'm curious if anyone knows about this, but I invite you too to have a look at this. It's quite interesting, where in M31 we're able for the first time to map the mass of the stellar halo. This is the first. We're going down to basically using data with Raj's team. We're going down to 30 mag per arc second square, and we made this plot. So very curious to follow it up.
Okay.
Other questions for Aaron? Charlie.
Aaron's point was this is the first prediction of variation in that quantity with both.
No, the prediction comes from Purcell 2007, and we just apply it to the observation.
No. Look at the diagram has red and blue lines, which are differentiated.
Yeah, for different bulks to total ratio.
Yeah,
That's a slight add-on to Purcell at that. So to be fair, it's really Purcell that gets the credit. Another question? All right, let's thank Aaron again.